Good afternoon, everyone, and thank you for attending our From Mechanical HMIs to Touch, Old versus New Technology webinar. My name is Danielle Correa, and I'm the Marketing Coordinator here at Epic. Before we get started, I just want to let you all know that you will be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel located in the webinar control panel, and we will try to get to them all at the end of the presentation. If we don't have time to get through all of your questions, we'll be sure to reply back to you by email. Also, we will be recording this webinar, and we'll be posting both the recording and the slides on our website and our YouTube channel. Our presenter today is Stephen Goodman, our User Interface and Cable Assembly Product Manager. Stephen is a mechanical engineer with a BS and an MBA, both from Northeastern. Most recently, he was running a startup manufacturer's representative firm serving the aerospace, defense, and industrial markets. Prior to that, Stephen spent more than 7 years as a product manager in the aerospace industry, working with customers to develop new products to meet their ever-changing design requirements. As the User Interface and Cable Assembly Product Manager here at Epic, Stephen works with customers to provide solutions to specific problems through design consultation and, where needed, the creation of specific designs. Additionally, Stephen is responsible for the overall effectiveness of the quote process and resultant business success. So without further ado, I will pass it over to Stephen.
Thank you, Danielle. Good afternoon, everybody. My name is Steve Goodman. I'm the product manager here for our user interface and cable business units. This afternoon, we'll talk a little bit about switching from a mechanical to a touch HMI device and ultimately comparing the old versus new technologies that exist. So first, our agenda. As discussed, we'll compare the old versus new HMI technologies that exist and show that there's been numerous and significant changes over the past 30 years. Next, we'll touch on the benefits of using a Kapton or Polyimide circuit as the parent material to mount your HMI device. Next, we'll do a brief review of some of our capacitive touch and touchscreen technologies, explaining the technology and some benefits to using them. Next, we'll actually go through a specific example of the impacts and what it takes to switch an existing membrane switch device to a capacitive touch device. Lastly, we're going to summarize the overall steps of what it's going to take to next-gen your SMART HMI device. So first, we're going to compare the old versus new technologies. So hopefully everybody remembers the first generation Nintendo Entertainment System. If you look carefully, this controller consists of hard plastic keycaps, elastomeric keys, two-piece housing, and it's very similar to a number of technologies that exist today. By and large, these technologies are still common today. We're still using membrane switches, PCB-mounted, normally open switches, tactile switches, elastomeric keypads, hard plastic keycaps, electroluminescent backlighting. These technologies all still exist today, and they are high reliability products, but when designed right and for the appropriate use condition. So over the last 30 years, there's been a number of breakthroughs in materials. And compared to those first generation devices, these technologies have numerous improvements, resilience to chemicals, UV exposure, a variety of improvements to environmental conditions, improvements in optically clear adhesives have paved the way for touchscreens to be used everywhere. Big picture, there's a number of technologies we can lean on today to drive cost out of your product, improve reliability, consolidate your package size, and ultimately help guide your user through an experience based on all these technologies. Some of the other benefits of the new and next generation HMI technologies include reductions in material costs. The same package size and product 30 years ago, we're able to drive cost out through new advancements in materials. You're also then able to reduce the footprint of your device, consolidate components. For example, one IC today may have done the job of 30 to 50 components 20 to 30 years ago. All of these compiled together enable these HMI technologies to be utilized with our embedded systems that we can help develop here at Epic. And the first step is really pairing your capacitive touch device with some microcontroller, embedding firmware, and then converting all of these requirements into an actionable device and plan for a smart device that can go out and sense, measure, overall improving the user experience. So next, we'll talk a little bit about when to use a Kapton polyimide circuit in your HMI technology. So first and foremost, flex circuits are everywhere. They're extremely common, but they're also common in the use of various HMI technologies. By and large, the typical and standard material used is a polyester material with some kind of screened, conductive, and or transparent ink. This left picture here shows a screened-on polyester membrane switch. These devices are low cost, and when designed right, they do the job. However, if you are looking for an ultra-high reliability device, some kind of unique requirements such as very fine trace widths, working toward a footprint reduction, there's a unique tail exit location on your device, or maybe even you have a requirement to embed or surface mount small package components, bicolored LEDs, ICs, etc. That's just simply not feasible with the old polyester technology. So when we run into this, we lean on an FPC or polyimide circuit. There's a number of benefits as discussed, but big picture, it's a very minimal cost impact for a small device. There's a typical rule of thumb we follow where it's really 20 square inches of surface area or less. It's really a more or less a cost neutral or minimal cost impact. When you get to large devices in excess of 20 or 30 square inches, that's when we see the cost impact start to really spread. So we actually had a project where we took an existing device and had some challenges mounting a bicolored LED on the surface of a polyester membrane switch. What we observed was a high rate of failure between the bond of that bicolor LED, creating open circuits and ultimately failures for our customer. So we went and redesigned this device, and for a very minimal cost impact, we're able to significantly increase the reliability. Secondly, the overall circuit resistance was decreased by 15x. Between pins 1 and 2 of this specific device, our measured open circuit resistance went from 31 ohms down to just about 2 ohms. So these devices and technologies are excellent for capacitive touch technology, where you're looking to consolidate, you're looking to improve reliability, and then even possibly add some kind of IC, a microcontroller, or any other surface mount component. Next, we'll talk about capacitive touch and touch screens and how they can be used on your technologies. So first, capacitive touch switches are everywhere. You look around, whether it's your smartphone, whether it's the dash on your automobile, or even your first generation iPod if you still have that. All of these utilize capacitive touch switches. The technology is very simple, extremely high reliability, and the best part, there are no mechanical or moving parts. What this allows is for a sleek and easy interface to clean that really brings products and devices into the next generation look and feel that a lot of our customers expect. The actual physical construction of a capacitive touch switch is shown here in this diagram. The bottom layer can be any kind of circuit. It can be a printed circuit board of your standard FR4 material. It could be an FPC circuit. Could even be a screened-on polyester type circuit. The key then is to incorporate conductive traces and copper sensor pads or conductive sensor pads that create the capacitance field that's then sensed and tripped. Going further outward from the circuit, there's a optically clear adhesive layer paired with an overlay that then forms the overall capacitive touch system. Big picture, these switches do not behave the same way as a normally open dome switch, tactile switch, etc. You must have a device that's able to sense the capacitance and sense the change in capacitance. So for you to go out and develop a new product, you're actually removing the dome switches on an existing membrane switch, but you need to then add some kind of microcontroller in your system. There's a number of benefits to utilizing capacitive touch technologies. One of the primary benefits and most common ways we can help bring new products to market for our customers is the improvements in backlighting. Without a dome switch in the way, or without a large tactile switch in the way, you're able to achieve a uniform, completely custom backlight configuration. Pairing these switches with a light guide film technology or other unique backlighting design truly creates a custom solution for our customers. One of the important considerations for these devices is if you're removing the dome switch, you're removing the ability for that real-time feedback. If you've ever operated a tactile switch or a dome switch, you're aware that as you depress that device, there's an audible click or some kind of tactile response. It can be a challenge if this isn't planned in your system. So what we try to do is pair the capacitive switch technology with some kind of LED, a backlighting design, or even an audible tone and a speaker to provide real-time user feedback when the switch is depressed. Next, we'll talk about the material properties used in your capacitive touch overlays. Now, a lot of the behind-the-scenes mechanical and electrical design parameters are never visible to the end user. What they see is an outside screen, maybe it's glass, some kind of hard-coated acrylic, polycarbonate, or even polyester. But the user is seeing that outermost layer. They're never seeing the circuit board. They're never seeing the sensor pads. And because of that, it's very important to consider the material properties and how it will behave in your system. All of these materials that I've touched on here have different dielectric constants. And why this is important is because the higher the dielectric constant, the easier it is to trigger the switch. Also as important is within your stack-up, any air gaps or inconsistencies in the stack-up can negatively impact the repeatability and overall performance of your switch. Next, we'll talk about the hardness and overall material properties, mechanical material properties of these capacitive touch materials. As we indicated before, the thicker the material, the more decrease in sensitivity you're going to realize. So because of this, one must carefully consider all the operating conditions, the use conditions, and the qualification conditions before selecting this material. A typical way of measuring hardness of these materials is using a standard pencil hardness test, where different hardness pencils are actually scratched on the surface, starting from softest to hardest until you're able to visibly determine a scratch or damage to the surface. The majority of the materials we recommend are in this 4H to 9H zone. Our preferred material is a hard-coated acrylic, which is typically between 4H and 6H on the scale. Tempered glass, which has one of the better dielectric performance values, is also the hardest. However, as we all know, glass is brittle, extremely rigid, and it can be difficult to machine and work with. So these are some of the options we can consider, but before you move forward with your final material selection, we strongly recommend doing testing. Abrasion testing is one way to assess the overall performance, and there's a number of different abrasion type tests. Next, we'll talk about what it takes to switch from your standard mechanical membrane switch to a capacitive touch. So, as we've discussed before, these capacitive touch switches are very similar to a standard membrane switch. The primary difference is the elimination of your dome switch, which is acting as a normally open switch in your system. What that creates is the need to add firmware and some microcontroller in your PCBA to be able to interrogate that switch, decipher status, and correlate that switch closure event to a command. Next, you must be able to detect when that switch closure event occurs, such as having an audible beep, having an LED illuminate, etc. One of the misconceptions with switching from a membrane switch to a capacitive switch technology is an enormous investment in materials, engineering, etc. But in reality, it's quite a minimal cost impact to switch. These off-the-shelf microcontrollers, and obviously depending on quantity, can be very cost reasonable. Some of these range from just a couple dollars to even less depending on quantities. So the goal would be to design and develop a PCBA that consists of your microcontroller, some interface that can then interact with your capacitive touch sensor keys, potentially send this information to a third-party type display, incorporate a standard GPIO or I2C type interface, and then, most importantly, having access to this to debug and test the device. So we've included a small demonstration CCA here in the presentation to show a very rough block diagram of some of the devices that we've designed to help bring our customers' products to market. Next, we'll talk about touchscreens. As we touched on earlier, touchscreens are everywhere. Your smartphone utilizes a touchscreen. A lot of the new technology laptop devices have touchscreens. Even the display in your vehicle may have a touchscreen. But there's generally two major types of technologies that we lean on to provide this capability to our customers. The first and least expensive is a resistive touch technology. This consists of two conductive and flexible sheets with a very thin air gap in between the two. This requires force or actually pressure to be placed on the screen, creating an electrical path between those two surfaces, closing the circuit, which then correlates to a resistance value on the screen, which gives you your XY location and allows you to have a functional touchscreen. There's a number of different wire designs also. What that means is it's the shape and orientation of the sensors within the display. Those consist of a 4, 8, and 5 wire design. The 5-wire design is the most common, and these devices do require calibration to be operational. The next type of device is your PCAP, or projective capacitive touch device. This really is the majority of the devices out there today, such as your iPhone. And how these work are pairing a glass overlay with some sort of transparent conductive coated material on the back side. And the way these devices work is they're continually sensing for a change in capacitance at a certain location on the screen. That change in capacitance then correlates to a very specific XY location on the screen. The benefits to using an off-the-shelf product or an existing design product are some of these actually have the microcontroller necessary to operate the device embedded on the flex tail. Other considerations are, when you are starting out, it's best to lean on an existing off-the-shelf design where possible. Custom versions are possible, but you may run into longer lead times, minimum order quantities, which all correlates to program risk and additional cost. So what we recommend is to work together to try to identify an off-the-shelf product that meets the very specific resolution or size requirements that you need. In addition, your PCAP display can work with multi-touch operation, can actually work with gloves. We've had recent projects where we've had a firm requirement to wear 2 sets of latex rubber gloves and operate our capacitive touch devices. Lastly, if moisture or water is going to be present in the application, care must be taken to select the right device, microcontroller, to make sure that your device will work if your hands are wet, etc. Next, we're going to talk through the steps to bring your SMART HMI device to the next generation. So, a lot of customers come to Epic with an existing product. This product is in a variety of stages. It could be a 30-year-old legacy design. It could be a prototype. It depends. But for Epic to be successful with our customers and our partners, we rely on you to truly understand your existing design. So we strongly recommend to make sure that everyone completely understands the existing mechanical design, electrical design, so that we can understand our current condition and then work together to assess ways to bring that forward to the next generation. Secondly, the review of samples and existing technologies is vital, because the worst thing for us is to develop a product that may take 2 months to 2 years and our customer doesn't appreciate or isn't what they're looking for. So we work with our customers to demonstrate examples of these devices, get samples, so that you, the end customer, can decide on the best technology, the best material, all of which have cost and lead time impacts to bring your product to market. So once our customers have a firm grasp of what they want and what they already have, the next step is to work together on a detailed requirements matrix. The big takeaway on this is to truly understand our customers' must-have versus nice-to-have requirements. Why this is important is because a clean delineation between the must-have and nice-to-have requirements really helps both parties work together to develop a cost-effective solution in a timely manner. We all know us as engineers can make anything. The question is, can you make anything within the cost and schedule requirements that you're giving? So once it's clear what you want and the very specific requirements of that device, you must consider what the qualification requirements are to bring that product to market. If this is an aerospace product and it's going through environmental requirements, one would consider a DO-160 type environmental plan. For medical products, there's a number of existing IEC standards depending on the class of the medical device. But what this boils down to are EMI and EMC requirements, which drive shielding and component selection. These qualification requirements also drive product safety and ingress requirements like an IP67 rating. Also, depending on what the product is, there may be firmware or embedded system requirements necessary before you bring that product to market. And then the last real takeaway for how to bring your next-gen device forward is to have a robust plan for your firmware. Here at Epic, we work with our customers to develop the firmware for your embedded system. We work with you to review your requirements matrix, your existing design, and your must-have versus nice-to-have requirements to help compile all these into code and source code that will allow the device to function as you wish. And within this, another major concern and consideration is once this device is fully built and maybe a beta version of your firmware is available, we require our customers to thoroughly exercise this device in the end use case. There's tremendous amounts of information we collectively can obtain getting this device into the hands of your end customer, letting them evaluate it, letting them use it in the field, consolidating that information and getting it back to Epic so we can make any necessary improvements and revisions together to make sure your device operates the exact way it should. So one note, over the next few weeks, we will be releasing an additional piece of content on our website with the goal of providing an embedded systems requirements checklist that will help our customers go through all the steps necessary to bring this device to market. So with that said, the summary for this afternoon's webinar: our current HMI technologies offer a variety of high reliability solutions, and when necessary and where our customers need, can provide sleek and customizable features for our customers. Next, there is a number of existing technologies that we can lean on to help guide the user through the desired experience for our customers. These include backlighting, firmware customization, capacitive touch technologies, etc. And the last takeaway from today's presentation is that there are multiple cost-effective touchscreen and resistive touch type technologies available for your project. So with that said, I'm going to kick it back over to Danielle to talk a little bit about our products.
Thank you, Stephen. While Stephen reviews the questions that came in, I want to briefly mention some of the additional PCB-based products we offer here at Epic, including custom battery packs, flex and rigid flex PCBs, high reliability user interfaces, RF products, cable assemblies, and our energy efficient fans and motors. Next slide, please. All right, and I'll turn it back over to Stephen to go through some of the questions that came in.
Thanks, Danielle. Okay, first one here is, what are some recommended material options for a Class 2 medical device? Okay, well, I'm going to assume that this is capacitive touch. So with that said, for a Class 2 medical device, the outermost surface, the overlay material, is the one that the patient or the practitioner will interface with. Secondly, there'll be some kind of sterilization and EMI or EMC requirements that we imagine. One of the most common materials we lean on for this type of device are hard-coated acrylics or polycarbonates. These are cost-effective. They have a pencil hardness of between 4 and 6H. They're able to be wiped down. They also have a very reasonable dielectric constant, enabling a wide range of sensitivity options, giving your firmware developer and the microcontroller options when you bring this device to market. Okay, next one here is, can you talk about the firmware development process and how long it takes? So the answer to this is kind of difficult, and I feel I typically answer questions like this with a "it depends." So I can share some recent projects where we have developed or co-developed firmware, some of which have taken 2 weeks, others have taken 2 months, and others have much longer. And what this boils down to is there are times where it's not clear what our customer wants, so we try to work together to dial in on a very specific set of source code that meets all of our customers' expectation. So the actual process to do this is really, it's following the embedded systems checklist I talked about at the end here, but it would require a full understanding of what the device does, some kind of existing schematic or some kind of logic diagram, and then working together to turn that information into an actual circuit board or prototype board, selection of off-the-shelf surface mount components, and then writing some preliminary code and running the device. And depending on the level of complexity and the requirements, as I said, this could take 2 weeks, 2 months, or even 2 years. So it's a really tough question to answer, but the big picture is, depending on the complexity, the use case, there's a number of ways to attack that. So with that said, I want to thank everybody for attending my webinar this afternoon, and have a great afternoon. Take care.